Okay, here's the deal. All of these forces problems, these dynamics problems, you can tell it's a forces problem or that using forces and F equals ma is a nice way to approach it if they ask several things. Like for instance, if they ask in the problem something about friction, coefficient of friction in particular, you're going to have a hard time finding coefficient of friction without the friction equation, right? And if there's a friction equation, there's probably going to be F equals ma somewhere along the line. All right? If they ask about tension and normal force, okay, you're probably going to have to do a free body diagram and do F equals ma. All right? If they ask you for acceleration, remember that you've all had 2 years of physics already.
No.
So remember that, yes.
Unless, is Jocelyn still here?
You remember.
Wait, Gia hasn't.
It's okay.
Right. You remember last year when we talked about all the different types of ways to approach problems. We have kinematics.
Oh, our King's Hut.
That's right.
Huh?
We have kinematics. We have F equals ma. We had momentum.
You're not spelling.
We had energy.
You're not
Right.
spelling. That's a
I thought it was something eating chicken or something.
Yes.
King's, yeah. King's Hut.
King Tut eats
What was
chicken.
it? Chicken?
Okay, here you go. In mechanics, these are the 4 biggies. Okay? These are the 4 biggies. If you can decide which way to approach the problem, which way is the most appropriate from one of these 4, you're on your way to the promised land in 90% of the problems. Okay?
The Promised Land?
Yes, which is a 5.
Oh, okay.
Okay? The suburbs of the promised land is a 4. And the ghetto of the promised land is a 3. And you would like to at least live in the ghetto. Okay.
2 and 1 is my favorite.
All right, here we go.
At war with each other.
Now look, these are all vector approaches. By nature, vector approaches mean more math, right?
So don't
Because
do
you're
them.
talking about x and y direction, you're talking about vectors, you're talking about trig and geometry, right? If it's a scalar approach, like this, by nature it will probably be easier. Not always, but most of the time it'll be easier. So if you have a chance to solve a problem using energy and work, then you should use it, because it's probably easiest. But not all problems can you solve that way. So you got to do your best with what you got. So here's the deal. If it asks for a whole lot of forces and things like that, or if it asks for acceleration, you're probably in this category right here. F equals ma. Okay, what types of problems are a dead giveaway for momentum? Do you remember? Collisions are interactions of multiple objects, right? Interactions of multiple objects is probably momentum, impulse momentum, angular momentum this year, because that's the easiest way to solve it usually. Okay? Let's do the combined one first. How many forces act on it? What are the 3? Okay, this weight would be ma plus mb times g, right? Okay, what else? Normal force. And what else?
F push.
Okay, the force from the push. Okay? All right, now here's the deal. Looking at this, that's it, right? There's no tensions, there's no springs.
We have friction.
Do we have friction with the ground? Did I give you friction? I have it on wheels, right? So let's assume that there's no friction. We'll assume with our wheels we have no friction. All right, which way will it accelerate?
To the right.
Okay, we will assume that it will accelerate to the right. Notice I draw that off to the side, not attached. You can see that.
Oh, I see it. It's right there.
I'm telling you.
All right, now, step number 2, does it accelerate, yes or no? The answer is yes, but only in the x direction. So which way is our coordinate system going to be? Because we're lazy. It's going to be like this. X and Y. And the reason why we do that is because in the Y direction, what are all the forces going to do?
Cancel out.
They're going to cancel out. There's no acceleration in the in the Y direction, right? So that means, by default, this one and this one have to be the same. Okay? So those are the only two. And then that leaves us only with one thing left to do. And that's in the X direction, I have one force, the push force. And that equals MA plus MB, the total mass, times A. So I can find the acceleration of this thing. The acceleration is going to be the pushing force divided by MA plus MB. So if the question was, what's the acceleration of this thing? There you go. That's the easiest one to use, right? Because you can solve it right out. Okay, now let's look at this little one right here. How many forces act on the little one?
3. 4.
I have 3. I got 4.
I said 4. But I don't. I think it's. No, I think 3.
I think 3.
I got 3.
What are the 3?
Weight.
Normal push. Oh,
Okay.
little one.
Which way is friction?
Oh.
It's got to be up. What kind of friction?
Static.
Static. Uh-oh. Caution, danger, danger. Okay? That is less than mu force normal. Less than or equal to. That means that equation's of almost no use to us, right? Depending on the question. It's only going to be of any use to us if they ask us something like, well, what's the minimum force pushing this along so it doesn't slide? Well, then we're going to be at the minimum speed, therefore we're going to be at the maximum friction, and then this would be an equal sign. Okay? Does that make sense? If it doesn't say those special words like what's the limiting condition or what's the minimum speed to push it along so it just doesn't slide or just begins to slide, that's at the equal point. But anywhere else, we got nothing. All right? So be careful. Question mark. We don't know. All right. What else we got?
Weight.
We got weight. We got friction. What else?
Normal.
Which way's normal?
To the right.
Oh, normal's to the right. I'm going to call it force normal
A to B.
B.
from A on B. Okay? Force of A on B. All right, those 3. Now, this thing is not sliding downward, right? So, even though we don't know whether we can use this equation, we do know something really important.
They're equal to each other.
Which 2?
Friction and.
That one and that one, right? So there we go. We know friction has to be at least equal to mg. And so since static friction is lazy, it only does what's necessary. It will be only as big as mg. This number right here might be bigger, right? All right, and then so the acceleration of this block to the right, what will that be? Is that right? I skipped a step. That's F equals ma, just written A equals F over M. Okay? Now what do we know about this acceleration?
It's equal to the.
Has to equal this acceleration, right? Okay, so here's the deal. If they ask about the friction in here, then we need to separate this one from this one because we could find friction here, right? If they don't ask about the friction and just ask for the acceleration of the whole thing, this is easier, right? Okay, so the different free body diagrams tell you different things. If they're asking for the forces in between these 2 blocks, then you're going to need to separate them apart because that's the only way to find them. Okay? Because if you keep the blocks together, those forces become internal and they disappear, and I'll show you why in just a second. All right, so what about this? How many forces? Or just list them. What are they?
Weight.
Push.
Push. Does it have a friction? Normal force? Has another.
Yeah, it's 2 normal forces.
Yeah. Oh. Right. There are 3 forces. You're missing 2.
There's no friction.
Friction from the block.
Oh, yeah.
All right, everybody. Which way is the normal force on this one from block A?
That way.
Force normal from block B on block A. What about friction?
Is it down?
Downward. Okay, everybody, this is really important. This is where they're really going to start expecting you to get a little bit better with your free body diagrams, because they're going to take free body diagrams are multiple objects and they're going to split them apart. And when they split them apart, there's going to be equal and opposite pairs of forces. This force right here equals this force right here. Because block A pushes block B to the right, therefore block B is pushing block A back to the left. Okay?
Yes.
Since block B is getting friction up, keeping it from sliding, therefore block A is getting friction downward as block B tries to slide downward across it. Or block A is essentially sliding up relative to block B. So this one is equal to this one.
Wait, but that's
So wait.
that one is going to equal that one, and it's going to be more down, and it's going to be more up, so it'd be going into the ground. Does that make sense?
That's correct. So when little block B tries to slide downward, that means it's applying a force on block A downward, causing the ground to push more up on block.
So the normal force on block A is going to be greater than those 3 combined.
Now, listen. This is really important. I'm glad you're catching this. Over here, we know that the normal force on these 2 blocks combined has to be equal to M plus mg, right?
Yeah.
Over here, the normal force is equal to what?
Just that.
The sum of the forces in the y direction equal ma. But what's my acceleration in the y direction?
0.
0. So that means that the ups equal the downs.
Yeah.
Okay, everybody look. Force in the y direction equals 0. What are my up forces here? Normal. What are my down forces?
MAG.
M, A, G, and what else?
Friction.
Force friction.
So that's why.
What the heck? Look at this. This says normal force equals MAG and force friction. Over here, it says that normal force has to equal MA plus MBG. So what does that mean?
That's why force friction equals
Ah,
MVG.
this has to equal MBG. Now look, does it? Force of friction here equals this force of friction, and that force of friction happens to equal that, because it's not accelerating up or down. Does that make sense?
Yes.
Okay, it has to always come out that way. Always has to come together. Where your free body diagrams in one picture tell you one story, and your free body diagrams in another picture tell you another story. But when you combine those stories, they must mesh. Okay? They must mesh. If they don't mesh up, then you're in trouble.
Did you mess up?
Then you messed up. That's right. That was really bad. But physics lends itself to such horrible jokes like that. All right, you got it? Okay, let's look at the next one then. This is actually a really hard one. This would be a really good free response question, okay, in Physics C. Another question they might ask with this would be like, what's the minimum force here required to keep this from sliding? All right, and so the minimum force to keep it from sliding, you assume it doesn't slide, and you get this, okay? So you'd have to find the acceleration somehow, right? So we know the masses. So we got to go back over here, and we know that the acceleration has to equal this, right? And we would know that the acceleration over here has to equal this as well. Over here, the acceleration is going to equal what? F equals ma in the x direction. Well, we have a pushing force minus a normal force from B to A equals MA times A, right? And so you would have different approaches to finding the acceleration, different equations, and you would just use whichever ones they give you enough information for. Okay? There you go. So, you see how these can get really long and involved with a really simple start. Next question would be is, okay, but what if we push this thing with a lower force, so we get less acceleration? Then what's going to happen? That block's going to start to slide. Okay, so what changes if the block starts to slide? What changes here?
Friction, kinetic.
Okay, this friction is now kinetic friction, right? All right, so over here, all that changes is we would get, this would be kinetic friction, and since it's kinetic friction, that means that we can use mu force normal, and so we could take that and plug it straight in here. Okay, we could do that right off the bat because we know it's going to be an equal sign this time. All right?
But the force normal would be the one to the right,
The force normal is the force, this force, right?
which is equal to.
So we got to be careful. It's not this force normal. Right? Okay, what about over here? What changes?
Same thing, force friction.
Okay, this force friction becomes kinetic. So that's an equal sign now. And are these two now equal?
Yes.
Yes.
No.
It's sliding downward, right?
It's
So
not
which one's bigger?
MG.
Mg. So now we got this going on. We got the sum of the forces in the y direction equals Ma in the y direction. We've got an Mvg downward minus the force friction kinetic upward equals Ma for this little block downward. I picked down as positive so that I just put a positive acceleration in it. Okay? Now, can we use this equation? Can we keep them combined? They're sliding relative to each other, so this one is no longer valid. Okay? That one's no longer valid. It disappears. Now, technically, you could still use this equation in the x direction because they're not sliding relative to each other in the x direction, only in the y. But you're better off, since you have to draw these two anyway, just to keep them separate. Okay? All right. So depending on what they give you, you would approach the problem differently. The different equations you would use depending on what's available to you to use. Okay? All right. Let's go on to our next one. I don't think there are any of these types of problems on the e-homework that's due tonight, but it's on our next one. I think a couple of motions on the next one. All right, our next one looks like this. Excuse me. All right. Common questions would be what's the acceleration and what's the tension in the string. Now, assuming that the pulley is massless, has no friction, and the string is not stretchy, then we can solve this problem. Once this pulley gets mass, we're going to have a whole new set of issues to worry about. So we'll do that in a little bit. We'll do that for the next test. All right, so how many forces on M1? How many forces on M2?
4 forces on M1.
So that's 4. It's got tension. It's got M1G. It's got normal.
Friction.
And it's got force friction. And it's kinetic if it's moving, right? If it's static, then we would just know that this tension would equal that if it's static. But if it's dynamic, if it's moving, then this tension's bigger than this one, right? We okay with that?
Yes.
All right, over here, how many?
Tension and
Tension and M2G. Your ag force, not yet. All right, in this problem, since the pulley has no mass, these two tensions, are they the same?
yes.
Yes. Okay, once that pulley gets mass, those tensions won't be the same. Let me show you real quick why. If the pulley has friction or mass, look what happens. Here's the pulley. If you're pulling it this way and you're pulling it this way, there's tension in both directions, right? The pulley won't move if it has mass, if those two tensions are the same. One of them's got to be bigger to make it roll, right? Okay, since we have a massless pulley, then it takes no force to get it to move, so we assume those are the same right now. Okay, but in a couple weeks we won't. All right, which one's bigger here?
If it's moving, it's empty.
Moving mg, right? Okay, so we would call this way positive, right? And we'd probably call this way positive. And we would write our free body, our F equals ma as m2g minus t equals ma. Right, over here, in this same direction that they're moving together, then we would write F equals ma, where T minus force friction kinetic equals M1A. And in this direction, in the y direction, those two are equal, right? So we have two equations, probably two unknowns, tension and acceleration, and we can solve those, right?
Yes.
There you go. That really, really hard problem for pre-AP is not so hard now, hopefully. All right, let's go on to our next one, where we had a block like this and a block on top of it, and there was a pulley up here, and it sat on an incline. That pulley was attached. And what did I say? I said there was friction between the two, but no friction on the. No, you said there was friction. Friction on both?
Yes.
All right.
But okay.
Wow, if they really want to be mean, they'll call one have different coefficients of friction. Okay? Which could be possible. All right, I call this M1 and M2. All right, if the thing moves, well, hang on. Let's look at it. What if it doesn't move?
That means
Yeah, if it doesn't move, the problem's easier. That's for sure. Let's look at the blocks separately and assume they don't move first. That one and that one. First of all, which way do you want to set up your coordinate system? Even if it's not moving, it's probably best to set it up this way and this way, because if it starts to move, then you're all set up and ready to go. Okay? Because if it accelerates, it will accelerate this way, this way. Okay? All right, so we're going to set up our coordinate system like this, in parallel and perpendicular. All right, so let's look at M1 first. What are all the forces on M1?
MG down. Normal.
Which way is friction on it?
To the left.
Straight left?
No.
that way.
Southwest? Parallel left?
20 degrees south.
Okay, friction's that way. What else we got? Normal. What else?
Tension.
Oh, we got tension. All right. There we go. Excuse me. So let's draw this one next. What do we got going on here? Okay, which way?
Normal?
Wait.
Oh, they would.
Right?
Oh, we got two normals. We're gonna call this one, what do you call this one, normal 1?
Yes.
And therefore, there will be an equal and opposite normal 1 this way. Whoa, so that one equals this one, right?
Yes.
Now, these are the ones that students tend to miss the first time through. Okay? These equal and opposite pairs of objects interacting. If they're going to touch each other, they're going to apply normal forces to each other in opposite directions. And if they're going to be sliding or trying to slide relative to each other, they're going to have equal and opposite friction forces. So we're going to have a friction force as well. Call this friction 1. So we're going to have a friction force this way, right? And this one equals this one. They're the pairs. Equal and opposite pair. What else we got going on? 1, 2, 3,
The
4,
other normal.
5.
The other tension.
We got another tension. We got another what?
Normal.
We got another friction on the bottom. Now, which way is the friction on the bottom? See, this one is trying to slide up as this one goes down, right?
Yeah,
So this one's going to be sliding down relative to here, so it's going to be up. Force friction 2. Does that make sense? Because block number 2 is going to slide downward relative to both the little block and the plane. We're missing one.
Normal.
The normal force from the plane on this block. And I'm going to have that one go this way, and that's normal force. I'm going to call it normal force 2. Is that okay?
Yes.
Goodness gracious, look how many forces we got.
Yay.
Now, but look, do you see that it's the same 4 forces as over here? You've got an mg down, you've got a normal force, you've got a tension and a friction, but then you end up with that extra pair of normal and friction that pair up with these two, right? So it's not that big a deal. It's just being aware of what you're looking for. Yikes. All right, everybody. Here's where it gets fun. Our coordinate system is like this, parallel and perpendicular. I'd like for you to write F equals MA in the parallel and perpendicular direction for this one and for that one. What do they look like? Before you launch too far into it, parallel, perpendicular, or both? Any that we have to split up? Just the mg, right? So this one's got to be split up. And here's our theta. Did I give you this one hits this way is m2g sine theta. This is m2g cosine theta. Anyone in here yet longing for the days of Physics B? A little bit. Don't be intimidated. Don't be intimidated. Oh, we can do it. I see no work. Go ahead. What? Parallel, perpendicular. Oh, damn it. Okay. It doesn't matter. If it's moving, then we'll have kinetic friction. If it's not moving, we'll have static friction. Okay?
So wait, for the parallel right now, do you want it moving?
It doesn't matter. Just put force friction in. And if it's kinetic, then we can substitute in mu force normal. If it's dynamic, if it's static, we can't. But nothing here changes if we have static or kinetic friction, right?
Force friction.
Hey, listen, everybody. This takes effort. This takes, it always looks easier when I do it on the board. And if it looks challenging when I do it on the board, then you're totally, yeah, in trouble. Okay? You have to go through and figure it out. You can't watch me do it on the board and go, oh, that looks hard, but now I understand it. Because that won't translate on a test, much less e-homework. All right, here we go.
Force friction 1.
How many? Okay, what do we got?
Force friction.
Wait a minute, which way is positive?
Use that little thing like.
Yeah.
To the left. To the left
That you
and down.
just do it when you.
Ooh, now hey, let's pay attention to this one. Because which way is this one going to accelerate?
That
Up.
one accelerates.
Down. Which way is this one going to accelerate?
Up.
Oh man. And since their accelerations have to be the same, then we really ought to do this.
No.
Yeah.
That's all right, just change the sign and all. Piece of cake.
Who's erasing things?
No, don't erase, just change the sign.
I'll just give it to you how I have it on my paper.
That's why we do everything with pencil.
Then you can fix it.
We make mistakes all the time. It's part of science. It's called learning. All right, here we go.
Tension
Tension.
minus force friction 1.
M1G
Okay.
sine theta minus force friction 1 equals M1A. Right?
So the acceleration for both of them are going to be equal, correct?
Okay, will the acceleration for both the blocks be the same?
Yes.
It has to be. Well, we're assuming if the string isn't stretchy or anything weird, right?
Okay.
Okay, what about the perpendicular direction? What do we get?
Force normal 1 minus M1T cosine
Equals what?
0.
Equals 0. Now, everybody, do you see the reason why we set up our coordinate system this way? Because that's 0. Most of you will skip this step and go straight to this.
Equals.
I said I was gonna do.
Okay, so we know that this one equals this one. Hey, that's nice, because now we know this one equals this one, which equals this one. Right? So we can substitute that in if we need to, right? Here we go. So this is a piece of cake. It just takes a little effort. It's the first time you've seen it, so it looks weird. Okay, now this one in perpendicular. What do we have?
F normal 2
F normal 2
minus F normal 1
F normal 1
minus M2G cosine theta
equals
0.
0. Now most of you will skip this step. Most of you will skip this step, and you'll go straight to equals and get rid of the 0. That's fine. You'll put the positives on one side and the negatives on another side. And because we know this, Fn1 equals m1g cosine theta, we could plug that in right here, and notice what we get then. We get Fn2 equals m1g cosine theta plus m2g cosine theta. What does that mean?
You could put them less together.
We could combine those together, and we would end up with that the normal force 2 equals m1 plus m2 times g cosine theta. What does that mean? That means that the normal force has to hold up both blocks, which is what we would have guessed to begin with, right?
Yes.
That the normal force pushing up has to counterbalance the mass, the weight, in the cosine direction of both those blocks. What we would expect anyway. All right, let's do the other one over here in the parallel direction. This is going to have 1, 2, 3, 4 terms.
M2G sine theta minus force friction kinetic minus tension minus force friction
1.
equals MA.
There you go. I think I got the same thing. I got a couple terms swapped.
Okay.
Yeah.
I just put my frictions together. All right, so there you go. Now look, there's a couple things we could do. We could take tension out of the equation by solving that for tension and plugging it in here, if we wanted to. Or we could solve for acceleration and plug it in here. Alright, but that's ugly. They're going to have to give us a little bit more information before we can solve something like that, right? They have to give us quite a few things. Like they'd have to give us, if it's sliding, let's assume it's sliding. Alright, then this becomes m2g sine theta minus mu force normal 1 minus mu force normal 2 minus t equals m2a. Now look where this keeps going. Now we got to plug in the normal force, right? And what was the normal force? Right here, right? So this becomes m2g sine theta minus mu m1g cosine theta minus mu m, what's my normal force over here? M1 plus M2g cosine theta minus t equals M2a.
Yay. Beautiful.
Okay. Just keep going, going and going and going. I think we're probably done. I think there's much more we can do. All right. You could do that, right? Sure. Sure you could. Sure you could. All right, let's do something a little easier.
Which way?
All right. Okay, who wants to draw the free body diagram on the board?
Oscar wants to draw.
Who does?
Dylan wants to draw.
Okay, you volunteer. All right.
Oscar has to draw. He's gonna get up here and give it to you. Go, Dylan.
Dylan.
Get it.
So far, you're right.
It's massless.
Awesome. Great job.
It's too big.
It's right. The one side's a little wonky looking. Put a smart aleck. Tough crowd.
I know, I feel like I'm being crucified.
Yeah, I didn't pass up the tomatoes. You're in good shape.
It's not the tomatoes I'm worried about.
You're worried about sharp objects?
Yes. Dude, that would be awesome.
Like physics crucifixion.
What?
No.
I can't wait to
Oh my God.
No, Good. I love tomatoes. Oh, yeah. Oh, Michael Louder.
Yay. Great job.
All right, here we go. Looking good. Thank you, Dylan. All right, we have a normal force to the left. We We have friction down, it's kinetic because we know it's moving upward. I think I told you that last time. M1G down, assuming it's M1. The pushing force is this way. Dylan broke up his coordinate system to be something like this, X and Y. So he broke this up into X and Y components. So if we're going to write the sum of the forces in the Y direction equals MA, then that's going to be F push cosine theta minus force friction kinetic minus M1G equals MA. Right? Now, whether it's moving at a constant speed or not, this is the equation. If it's moving at a constant speed, what changes about the equation? Then this would be 0, and these forces, this force would equal these two, right? So it depends on whether it's accelerating or not. We just know it's sliding. All right, in the x direction, the sum of the forces in the x direction equals ma, but we know in the x direction there's no acceleration for sure. So we know that the normal force is equal to F, push, sine theta. Now, where else can we go with this? There's another step we can take it yet. Anybody see it?
Repeat that again, please.
There's one more simplification step we can do.
Force. I know what the friction.
The friction, since it's kinetic, we can substitute in
Force normal.
minus mu force normal.
Which is equal to F push.
But we know that is equal to that, and so we can plug that in, right?
Yes.
But that's because it's sliding. If it was static, then we could not make that substitution unless we knew that it was like right at the break point. Okay, that's as far as we can go. There's nothing else we can substitute. Did I do that right? Now, if it's accelerating, it looks like this. If it's moving up at a constant speed, this becomes 0. And then we can move on from there. All right? So there we go. All right, we got one last one. A lovely one. Lovely, lovely, very lovely.
I think we even got days like that one later. This didn't make sense to me. Yeah. That's just cool. That's just
All right, there's a force pushing this wedge to the right, and this little block stays.
That's on our e-homework.
It's a what?
That's on our e-homework.
Is this on our e-homework?
No.
No. Yeah, I know.
That is on our e-homework.
Oh, the record.
That's number 9, right?
Do it, please. I don't get it.
Work it, work it, work it. Hey, by the way, all the elevator problems, there's several elevator type problems. Just remember, there's like an mg down and there's like a normal force up, right? And the relationship of these two makes a difference for whether a person's accelerating up or down, right? If you're not accelerating, these two are equal. All right, so here we go. What does the e-homework question ask?
What's the acceleration of the wedge?
Okay?
Wedge blocks.
So, of the wedge block system. All right, so here we go. This is mass 1, this is mass 2. It's accelerating to the right, in my case. I think yours is accelerating to the left, but whatever. I'm not going to redraw it. All right, so wait a minute. How can we draw the free body diagram? Can we draw it together?
Yes.
We sure could, and if we draw it together, it's going to look like this. We have one force this way, and what else? What else we got?
No, it's word.
We got M1 plus M2G, and we got a normal force, right? Where these are equal. So F equals MA. where F equals M1 plus M2A. Unfortunately, they don't tell us what F is, do they?
No, he was in one either.
They don't give us M1 either?
Yeah.
Oh, rats. All right, let's get going. How much time we got?
5 minutes.
5 minutes. All right, this is not going to help us out, it looks like. So let's separate them out. Here's M2. Here's M1. Okay? Excuse me. Oh man, which way is the acceleration in this case?
To the right. To the west.
It's
east.
Yeah, in my case, it's to the east, right? In your picture, I think it's to the west. So wait a minute. If our acceleration is this way, which way do we want to make our coordinate system?
That way.
Oh, this is a little different. We normally think of an incline where it'd be the coordinate system would be this way, right? So how many forces act on this thing?
Gravity.
We got an M2G.
Normal.
We got a force normal.
And it's accelerating.
Is there any friction?
No.
No.
That's it. Now, pay attention. Which way is it accelerating?
To the right. So it'll be.
So, how do we split up our coordinate system? Is this one X, Y, or both?
Y.
Y. Is this X, Y, or both?
Both.
Ooh, we gotta split this one up. There's our theta. That's the theta here. So that means that in the Y direction, we have the forces canceling, which means that M2G equals force normal cosine theta. And in the X direction, we have that force normal sine of theta equals M2A. You see how splitting it up in the direction of the acceleration helps us out here? It makes it a little easier.
Yes.
All right, what about in the Y direction here? What do we have? Well, actually, let's draw our forces. What do we have? We've got M1G.
Force normal.
We got a normal force this way, force normal. This is the same as this one, right? We got a normal force up this way. I'll call that normal 2. And we got a pushing force, right? I'll just call it F. Is that it? All right, in the Y direction, we've got 3 forces that account for no acceleration, right? So we have a force normal 2 up equals a force normal cosine theta down plus an M1G, right? By the way, that is equal to this, so the normal force 2 just equals M1 plus M2G, which makes sense, right?
Yes.
That should make sense. Because I substituted this in here. All right, in the X direction though, that's probably going to be more helpful. We have a F equals MA, so we have a F to the right. And what else do we have?
Minus.
We've got a minus
Force normal.
normal force sine theta equals M1A. We got this one right here. Now, what did they give us in the problem?
Mass of the block.
Which block? Both of them?
No, the one that rests on the wedge. The angle and acceleration.
And acceleration.
Yeah, we got it.
Do we have it?
I mean gravity.
Oh.
Gravity.
Do they give us A?
No.
Draft.
We're trying to find it.
Yeah.
They don't give us F?
No.
Nope, those are the only things they do.
Is it multiple choice?
Bonus,
Leading.
nope, Mr. Bruin.
Okay, we've got this equation here. And we got these 2 equations here. I think that's enough. They give us theta. We don't have normal force.
Just have to substitute a lot.
Substitute this in, but we don't have what M2 is.
But then you can move to the other side, factor out.
Can we use these three equations?
Yes.
Because look, we have M2, we have theta, M2, theta. I think I have 4 unknowns.
No, I think you can do it.